In this lesson, we'll be learning about sequences. So a sequence can be thought of as a list of numbers written in a definite order. Usually, the notation that we're going to use for this will involve a's with subscripts. A sub 1 refers to the first number, a sub 2 is the second number, etc. Now, notice for every positive number n, there is a corresponding a sub n. And alternatively, another definition for a sequence is it can be defined as a function whose domain is the set of all positive integers. And what would a graph of this function look like? So what we'd have is some function f of n equals a sub n. That's what the function is. And so f of 1 gives us a1. F of 2 gives us a2, or the second element. And the domain of this function is just all positive integers, meaning you only plug positive integer numbers in. So you plug in 1, 2, 3, etc. And suppose a1 is up there, a2 is down here, a3 is up there. It's going to be a collection of dots. So 1 dot for a1, 1 dot for a2, 1 dot for a3. Unlike what you're used to accustomed to with functions is continuous functions where there's lines connecting those dots. In this case, there are not. So list the first three terms of the following sequences. So often you're given an equation that defines the terms for you. In this case, we have that an is 2n over n plus 3. So a1 is what you get when you plug in 1. 2 over 1 plus 3 is 2 over 4 or a half. A2 will be 4 over 2 plus 3, which makes 4/5. And a3 will be 6 over 3 plus 3, which makes 1. So there are the first three terms of that sequence. The next one, we have cosine of n pi over 2. So a1 will be cosine of 1 pi over 2. So think about your unit circle. Pi halves is the point right there. Its coordinates are 0, 1. At that point, cosine is the x. It is 0. A2 will be cosine of 2 pi over 2, which is cosine of pi. And that's this point right here. That point has coordinates negative 1, 0. The cosine is negative 1. A3 will be cosine of 3 pi over 2. That's this angle right here. At that point, the coordinates are 0, negative 1, and the cosine is 0 again. So our first three terms are 0, negative 1, and 0. Now, functions can also be defined in a manner that's called a recursive definition. And what this means is that the next terms depend on the previous terms. So this example we're doing right now is a pretty common example called the Fibonacci sequence. So the first number is defined to be 1. The second number is also 1. And the nth term is the sum of the n minus first term. So that's 1 previous. Notice that n minus 1 is 1 less than n. And then n minus 2 is 2 terms previous. So it's the sum of the previous 2 terms. So a sub 3 would be a sub 2 plus a sub 1, which will be 2. A sub 4 will be a sub 3 plus a sub 2, which is 1 plus 2, or 3. And a5 is a 4 plus a 3, which would be 5. And the pattern continues. A sub 6 will be 8. A sub 7 will be 13. You get the idea. But the first 5 terms are 1, 1, 2, 3, and 5. Here's another less famous example. This is just a goofy one. So the first term is 6. Now this says that the next term is found by taking the previous term divided by 6. So a2 will equal a1 over 6, which is 6 over 6, or 1. So first term is 6, second term is 1. a3 will equal a2 over 6, so 1/6. a4 will be a3 over 6, so a 1/6 over 6. Notice that that is the same thing as 1/6 times 1/6, or 1/36. And the last term, a5, is a sub 4 over 6, so 1/36 divided by 6, or 1/36 times 1/6, which is 1 over 216. So there are your first 5 terms. Now we are going to focus a lot of our time in this lesson finding the limits of sequences. So the limit of a sequence, so we're supposing that L is a real number, and the limit of a sequence A sub n is L, written like this. Here's the very technical definition. We'll talk about it a little bit in layman's terms as well. If for every epsilon bigger than 0, there is a positive number m, such that the absolute value of a sub n minus L is less than epsilon, whenever n is bigger than or equal to m. So first of all, what this is saying is that the distance from a sub n to L is smaller than that epsilon. So what this looks like is this, is you have some number L, and the terms in your sequence kind of bop around, they go back and forth, but you're thinking that eventually they're going to start getting pretty close to L. What this definition is saying is that you suppose you have some enemy, and the enemy picks a really small epsilon. So there's minus epsilon plus epsilon. And you say that eventually the distance between your points in your sequence, your terms in your sequence, and that limiting value is going to be smaller than that epsilon. So your adversary gives you this epsilon, and you go out there and you do some work and you figure out, okay, well, if I'm bigger than some value m, where m is 1,000,000 or 2,000,000, then from that point on, my points in my sequence are less than that distance away from L. Another way to think about this is eventually, as the values of n get larger and larger, the values of in your sequence get closer and closer to L. This is just a way of formally saying that exact statement. And you find limits of sequences pretty much the same way you find limits of functions. But before we get there, we're also going to do a little bit of pattern recognition, trying to find patterns for sequences. I'm afraid there are no super awesome hard fast rules here. It's just helpful to look for patterns and guess and check until you can get something that's correct. So my sequence is 5, 8, 11, 14. This one's pretty simple. You can see to get from one term to the next, you're adding 3. So if A1 is 5, what number? So we plug in 1, we have to get out 5. So we have something plus 3. Well, I think 2 plus 3 would make 5, and then you could think A2 is 2 plus 3 times 2, so 6 plus 2 makes 8. And the general form here for the nth term will be 2 plus 3n. All right, this one's a little bit less obvious. You see that there's obviously some powers of 4 in the denominators. You got 4, 16, and 64. And then also we have some negative flip-flopping happening. So an. So first of all, to get the negative flip-flopping, if you make -1 just to the n, that means when you plug in 1, your first term would be negative. That's not the case here. So let's make that n plus 1. Then when you plug in 1 for n, you get negative 1 to the second, which makes that first term positive. Okay, so then denominators. So this is the fifth term, and it appears to be 4 to the third. And this is the fourth term, it appears to be 4 to the second. So this could be 4 to the power of n minus 2. So think 4 to the third, 4 to the second, 4 to the first. And let's see if that works out for the other terms as well. So if I plug in 1, I will have negative 1 squared over 4 to the 1 minus 2. That's the same thing as 1 over 4 to the negative 1, or 4. So our first term matches up. A sub 2 will be negative 1 to the third over 4 to the power of 2 minus 2, which is 4 to the 0 or 1, so that makes negative 1. So this appears to check out for at least the first few terms. That is the pattern that you will have, or the general A sub n. So now let's talk about how to find limits of sequences. So suppose we have a real number L. Suppose f is a function of a real variable x such that the limit as x goes to infinity of f of x is L. And if you have a sequence such that f of n equals a sub n for every positive integer n, then the limit as n goes to infinity of a sub n is also L. So here is the relationship. Suppose you have some function f of x and it's approaching some limiting value L. What this theorem says is that if you have a sequence where the terms of that sequence are found by plugging n's into that function, that the limit of the dots and the sequence is the same thing. What this lets you do is find limits of sequences the exact same way you find limits of functions. For example, suppose we have a sequence b sub n equals n squared over 2n squared minus n plus 5. So we're going to find the limit as n goes to infinity of b sub n. If this limit goes to a specific number, we'll say that our sequence converges, and if it goes to infinity or fails to go to one place, as in it, like say, bops around between negative 1 and 1, then we'll say that it diverges. So here, when you have a ratio of two polynomials, the trick is to divide by the highest common power. So in that case, we're going to multiply by 1 over n squared, which is the same as dividing by n squared. So that's the limit as n goes to infinity of 1 over 2 minus 1 over n plus 5 over n squared. And now you can say that as n gets large, this 1 over n is going to go to 0, and this 5 over n squared is going to go to 0. So in your limit, as n gets big, you're approaching 1 over 2. So this sequence converges to 1/2, which means as the n's get large enough, eventually your values in b sub n are going to get closer and closer to 1/2. Another rule you had for finding limits of sequences was this rule called L'Hopital's rule. So let's find the limit as n goes to infinity of e to the n over n squared. Technically, L'Hopital's rule only applies to functions, so you technically have to change those n's into x's to show me that you understand that. I'm not going to be really picky about that, but I have to do it to be a good mathematician in the video lectures. So I think I have an infinity over infinity limit here. And when you have a limit that's infinity over infinity, L'Hopital's rule says that the limit is the same thing as the ratio of the limit of the derivatives. So the limit of e to the x over x squared is the same thing as the limit of e to the x over 2x. Notice I didn't do the quotient rule, nothing funny like that. I just took the derivative of the numerator, the derivative of the denominator. That's what this rule says. Now notice as x goes to infinity, the numerator still goes to infinity, and so does the denominator. So this is another infinity over infinity limit. We're going to apply that rule again. The derivative of e to the x is e to the x. The derivative of 2x is 2. And that limit, as x goes to infinity, will be infinity over 2, which is still infinity. So this means that as n gets larger and larger, the terms in this sequence keep getting bigger and bigger and bigger. This sequence diverges. It fails to go to a specific number. This next example is a slightly tricky application of L'Hopital's rule, so bear with me. This will probably be more like a homework question or a take-home quiz question, but not a in-class exam question. So we're going to find the limit as n goes to infinity of 1 plus 1 over n to the power of n. Okay, I'm going to start that by letting y equal 1 plus 1 over x to the power of x. And then I'm going to natural log both sides, and I'll take, say, ln of y is ln of 1 plus 1 over x to the power of x. And rules for logs tell us that that power can now pull down. Okay, so there we are. Now, the limit as x goes to infinity of natural log of y will equal the limit as x goes to infinity of natural log 1 plus 1 over x times x. Now, this thing, the natural log of 1 plus 1 over x, that's going to ln of 1, which is 0, and x is going to infinity. Technically, 0 times infinity is not actually always 0. Occasionally, 0 times infinity equals a number. It's weird, but it happens. So there's a trick you can use to convert this into a form where you can use L'Hopital's rule, and here is the trick. Limit x goes to infinity, natural log of 1 plus 1 over x, and that's divided by 1 over x. That is a tricky trick to come up with on your own, but what I should expect from you is that having seen it, you understand that it's true. So notice that was what you had inside your limit to start with, and I moved that x to the denominator by making it into 1 over x. You could verify that this was correct by multiplying by x over x. You'll get that the x's in the denominator cancel, giving you back what you had. So that's a legitimate trick and it works. And the reason that you have to do that is because now as x goes to infinity, your numerator goes to ln of 1, which is equal to 0. And your denominator, 1 over x, that also goes to 0. It's of the correct 0 over 0 form so that L'Hopital's rule can be applied. So that was the reason we had to manipulate the limit. Look at the expression like that. So we made it the right form. Okay. So now we apply L'Hopital's rule. The limit as x goes to infinity. So the derivative of ln of that stuff will be 1 over that stuff times the derivative of the stuff, which is negative 1 over x squared, all over the derivative of 1 over x, which is also negative 1 over x squared. And look at how lovely that is, those negative 1 over x squareds cancel. So the limit as x goes to infinity of natural log of y, that's equal to the limit as x goes to infinity of 1 over 1 plus 1 over x. So that limit is equal to 1. All right, now here's the tricky bit. You found that the limit as x goes to infinity of ln of y is equal to 1. You want to find the limit as x goes to infinity, technically, of just y. So that limit can actually move inside of that natural log. The technical reason is because ln is a continuous function. So you sort of flip-flop the limiting and the logging, and that lets you solve for the limit of y. So exponentiate both sides now, and the limit as x goes to infinity of y, which is the original expression, 1 plus 1 over x to the x, will equal e. I totally get that those are tricky. You're supposed to do a couple on your homework. Other than that, it probably won't be tested other than a take-home quiz. Determine whether the sequence an, where an is as defined below, converges or diverges. If it converges, find its limit. All right, so we're going to use a similar idea here. The limit as n goes to infinity an. So limit n goes to infinity of cosine of n pi over n plus 1. So as cosine is a continuous function, this limit can move inside of it, and that becomes cosine of the limit as n goes to infinity of n pi over n plus 1. And n pi over n plus 1 will approach pi as n goes to infinity. And cosine of pi is -1. So our sequence converges to -1. In this next example, we're also going to use the continuity of natural log to move the limit inside of it. It's just not obvious how, unless you remember your rules for natural logs. And the rules for natural logs that you should know state that if you have natural log of a minus natural log of b, that's the same thing as natural log of a over b. So this tells us that a sub n could also be expressed as ln of the quantity n plus 1 over n. So now let's find the limit as n goes to infinity of an. So limit as n goes to infinity of natural log of n plus 1 over n. The limit can move inside the ln, so ln of the limit. And as n goes to infinity, n plus 1 over n approaches 1, because the degrees of the numerator and denominator match. So you have ln of 1, which is 0. So our sequence converges to 0. So that means as you plug in larger and larger numbers for n, the result you get for a sub n is getting larger and closer to 0. Now, a lot of things that we're going to use in this unit will involve something called a factorial. So the symbol n followed by an exclamation mark isn't a really happy variable. It is called a factorial. And it is defined for positive integers. By definition, n factorial is 1 times 2 times 3, all the way up to n minus 1 times n. So it's all of the integers up until n multiplied together. And by definition, 0 factorial is defined to be 1. There are reasons to do that, so just remember that 0 factorial is 1. So for example, 5 factorial, that is 5 times 4 times 3 times 2 times 1. You could also think about it as 1 up to 5. It helps me think about it as this number on down. So that will be 20 times 6, or 120. Now notice between C and B, the only difference is that there's a lack of parentheses in B. So for B, this means 2 times n factorial, as in do n factorial first, then multiply by 2. So that's 2 times n. 1 less than n is n minus 1. 1 less is n minus 2, all the way down to, say, 3, 2, 1. So that's what 2n factorial is. Now 2n, the quantity factorial, would begin at 2n. 1 less than 2n is 2n minus 1. And then 2n minus 2, all the way down to 3, 2, 1. So this part C is quite a bit larger than part B. If you wanted to prove it to yourself, let's just do some small number. Let's do 2 times 3 factorial. and then 2 times 3 factorial. So here we'd have 2 times 3 times 2 times 1, which would give us 12. Here, 2 times 3 first makes 6 factorial, and 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. We figured out that 5 factorial is 120, so we really have 6 times 120 here, which is, holy moly, 720. So much, much, much larger. Those parentheses really do matter. So we're going to determine whether the sequence an, where an is defined as 2n minus 1 factorial over 2n plus 1 factorial, converges or diverges. Now, a useful way to think about factorials is that the number inside the factorial tells you where to start counting down from. So, for example, you could think about 5 factorial as 5 times 4 times 3 times 2 times 1. You begin with 5, the next number is 1 less than 5. So 2n minus 1 factorial will begin with 2n minus 1. 1 less than 2n minus 1 is 2n minus 2. And then 2n minus 3. All the way down to whenever you get 3 times 2 times 1. How many numbers you will have in that numerator depends on what number you are plugging in for n. On the denominator, the first number is 2n plus 1. 1 less than 2n plus 1 is 2n. 1 less than 2n is 2n minus 1. 1 less than that is 2n minus 2, all the way down to 3 times 2 times 1. And notice that there is massive cancellation happening here. So this 2n minus 1 cancels with that 2n minus 1, and etc. Everybody in the numerator cancels with something in the denominator. And that tells us that this a sub n simplifies to 1 over 4n squared plus 2n. And so now that we know what that expression simplifies to, we can find the limit as n goes to infinity of an. It will equal the limit as n goes to infinity of 1 over 4n squared plus 2n, which is equal to 0. Now, another theorem we had for sequences for finding limits was this thing called the squeeze theorem. And so the basic idea is this. You have 2 different sequences, and their limits are both L. And you know that the terms of one sequence are always less than or equal to the terms of the other. So here's my an. Ish. And there's my bn. Notice the terms of bn are always bigger than or equal to an. And the terms of cn live somewhere in the middle. Maybe they bop around a lot, but they're stuck between them, or they're squeezed between the blue and the red dots. And this theorem says that if this is true, limit as n goes to infinity of the c's is also L. So if you're going to apply this theorem, what you'll have to do is find something that your sequence, which will be the Cn, is sandwiched in between. And then the limits of the things that it's in between will both go the same place, and therefore the limit of your sequence will also go to the same place. And a really common application of this is trigonometric functions, because some of them are bounded. So for example, we have inverse tangent of n over n. Now, inverse tangent of n looks like this. It has horizontal asymptotes at y equals positive pi halves and y equals negative pi halves. And so what that means is that inverse tangent of n is less than or equal to pi over 2, but bigger than or equal to negative pi over 2. As in, it's stuck between those two things. Now what I'm going to do is take this inequality and divide everything by n. And with sequences, our n's are always positive, so we're dividing by a positive number, and we don't have to worry about the inequality signs flipping. So I have negative pi over 2 over n is less than or equal to inverse tangent of n over n, which is less than or equal to pi over 2 over n. So notice how tangent inverse of n over n is now sandwiched in between two things. And also, what you can say is note that the limit as n goes to infinity of pi over 2 over n, well, that's 0. And the same thing is true for negative pi over 2 over n. That limit is also 0. So both the sandwich sequence on the top goes to 0 and the sandwich sequence on the bottom goes to 0. So that tells you that thus the limit as n goes to infinity of inverse tangent of n over n is also 0. So find two things that your function is sandwiched between. The limits need to be going to the same place, and therefore the limit of your function is also the same thing. All right, another application of the trig function. 2 to the negative n times cosine of n pi. This is the same thing as cosine n pi over 2 to the n. Now the thing to note here is that as a function, cosine is actually bounded. The highest value of cosine is 1, and the lowest value is negative 1. And the number inside the cosine, that pi, will affect the speed at which this cosine curve oscillates, but will not affect its amplitude. So you know that cosine is in between negative 1 and 1. So then negative 1 over 2 to the n is less than or equal to cosine n pi over 2 to the n, which is less than or equal to 1 over 2 to the n. And then as the limit as n goes to infinity of, I'm going to say plus or minus 1 over 2 to the n. Well, think about what happens that you plug in really big numbers for n, you get 1 divided by a humongous number. That's going to make 0. You know that the limit as n goes to infinity of cosine n pi over 2 to the n is also 0. So don't be confused and think that squeeze theorem problems also always involve the limits being 0. That just happened to be the case for the couple examples that I chose. Now we're also going to deal with sequences that are something called monotonic. Now a sequence is called monotonic if its terms are non-decreasing or non-increasing. So what this means is that subsequent terms are less than or equal to the previous terms. So this first sequence, second sequence, so monotonic increasing, monotonic decreasing. So the terms are either staying the same or getting larger, staying the same or getting smaller. To determine whether a sequence is monotonic, you could look at a few of the first terms, and if it's obvious, you can make a statement. And if you have a suspicion, you may have to prove it using some ideas from Calculus 1. So this first one is one of those obvious ones. So find A1. A1 will equal 5 plus negative 1 to the first, so 5 plus negative 1, which will be 4. A2 will equal 5 plus negative 1 squared, or 6. A3 will equal 5 plus negative 1 cubed, which is 4. And you can see that this pattern is just going to keep going. So this sequence is going to be the list 4, 6, 4, 6 from now until all eternity. So are the terms in this sequence either non-increasing or non-decreasing? And the answer is no. This is a sequence that is not monotonic. And there, in that example, there's a pretty obvious pattern. You can just list the first few terms, say what's happening, and you're good to go. Also, just as an aside, this is an example of a sequence that does not converge, or you could say even diverges, where it does not diverge to infinity. So a sequence that bops around and goes 4, 6, 4, 6, 4, 6 forever and ever also doesn't make up its mind as to where to go, and that also is a divergent sequence. So diverging doesn't have to mean that your terms go to infinity. Okay, now with this next one, let's try to see if we can figure out what's happening here. Just we'll take first few terms and guess and see what we think is going on. So B1 will equal 3 over 3, which is 1. B2 will equal 6 over 4, which is 3 halves, or 1.5. B3 will be 9 fifths, which is 1.8. B4 will equal 12 over 6, which is 2. And B5 will be 15 over 7, which is approximately 2.14. So at least from this pattern, it appears to be the case that my terms are actually increasing. Now the question is, how do you prove that? Now proving inequalities is a little bit tricky, and I think that the best way is to actually use calculus and to use a derivative. So here's how we're going to do it. Define a function f of x as 3x over 2 plus x. Remember that functions are increasing if their derivative is positive, and they are decreasing when their derivative is negative. So we're going to find this derivative of this function. So we have to use something called the quotient rule. So that will be low d high minus high, derivative of the low function, all over low squared. So simplifying slightly, this is 6 plus 3x minus 3x over 2 plus x, the quantity squared, or 6 over 2 plus x squared. Now for sequences, we only care about positive x's because the only numbers we plug into sequences are positive n's. So in this case, if your x is bigger than or equal to 0, does it make sense that f prime of x is always positive? You think about that, you take some number, you add 2 to it, and then you square it. That makes a positive number. And so now you know that as f prime of x is bigger than or equal to 0 for 0 to infinity, your sequence of b sub n's is increasing. And that's another way, it's a fancy way of saying increasing monotonic. Now some more definitions. So a sequence is bounded above if there is a real number m such that the terms of that sequence are always less than or equal to m. So if you have some sequence and some number above, that sort of fences them in, that sequence is bounded above. And similarly, a sequence is bounded below if there is some fence below it that pens all the numbers in. And a sequence is called bounded if it's bounded both above and below. So here we have our lower bound, here we have our upper bound, and the sequence's terms live between there. So the example of the sequence that we had that went 4, 6, 4, 6, 4, 6, that's an example of a bounded sequence. And a good example of a lower bound would be 4, and upper bound could be 6. And relating those two definitions together is the theorem for bounded monotonic sequences. So if you have a sequence AN and it's both bounded and monotonic, then it has to converge. So for example, suppose you have some sequence that's bounded above and it's monotonic, so the terms are either increasing or they stay the same. Eventually, that has to converge to something. That's what this says. So we can use this to prove that certain sequences are converging. So for example, here, we could find this limit using our other methods, but this method of showing that it's monotonic and bounded also works. So we took, in a previous example, we found this sequence A sub n is actually increasing. And as that is true, this is bounded below by A1, or its first term, which is 3 over 3, or 1, and bounded above by, well, the way I found an upper bound was I took the limit as n goes to infinity of the ANs, and that was equal to 3. So it's bounded above by 3. Any number bigger than 3 would also be something that is bounded above by, so you could have also said bounded above by 4. Bounded below by 0 would have also worked. 1 and 3 are examples of the least upper bounds. All right, determine whether the sequence with the nth term is monotonic and whether it is bounded. So let's just find the first few terms here. A1 will be 4 plus a half, so 4 and a half. A2 will be 4 plus a quarter, so 4.5, 4.25. A3 will be 4 plus an eighth, so 4.125. I think from here it's pretty obvious that this is actually a decreasing function. You could prove it by using the derivative. So if you let f of x equal 4 plus 2 to the negative x power, the derivative of that function is 0 plus negative 1 times natural log 2 times 2 to the negative x. This ln of 2 comes from the derivative of the function a to the x. And so that's the same thing as negative natural log 2 over 2 to the x. Well, that denominator is always positive for positive x's and actually any x. The numerator is negative. This thing is less than 0. And so thus f is decreasing. So the a sub n sequence is also decreasing. So this sequence, yes, it is monotonic. Specifically, it's a sequence that is decreasing. And is it bounded? Well, I think yes, it is. It's bounded above by 4.5. And think about the below. What was happening to these numbers? So 4 to 4.5, 4.25, and then 4.25 to 4.125. What you can see is that the number that you're adding to 4 is getting halved each time. So this is going to be bounded below by 4.